here's what we're talking about. A function in the form, we've got P of x over Q of x. Okay, P and Q are just polynomial functions. Okay, we're just talking about what we've been dealing with, are rational functions. Rational functions have a polynomial in the top, a polynomial in the bottom. Sometimes technically it's not really a polynomial in the top. It doesn't always have a variable in the top, but it absolutely has a variable in the denominator. So that's nothing new, but we're just going to use the P's and the Q's here in a minute, okay? So step one with this is you want to simplify the function. So factor and cancel, all that good stuff. After you simplify, we find the x-intercepts of the function by setting the numerator equal to 0. Here's why. Let's think about this for a second. If you are on the x-axis, okay, what is true about any point that's on the x-axis? The y value is 0, right? So the function is equal to 0. Our function is a fraction. So if a fraction is going to equal 0, which part of the fraction equals 0? The top or the bottom? The top, because if the bottom equals 0, it's undefined. Okay, so that's why our x-intercepts come from setting the numerator equal to 0. Because if we're on the x-axis, our y value is 0. That means our function equals 0. The only way that's going to happen is if the numerator equals 0. All right. Then we have something called a vertical asymptote. Okay, a vertical asymptote. We find that by setting the denominator equal to 0. Okay, vertical asymptotes are where the function is undefined. Okay, where f of x is undefined. That's what an actual vertical asymptote is. Okay, it is an x value. When you plug it in, it causes you to divide by 0. Okay, x causes divide by 0. Okay, the x value causes you to divide by 0, which we are not allowed to do. That's why we set the denominator equal to 0. Okay, vertical asymptotes, you also never touch. You never touch a vertical asymptote. Your graph will never touch a vertical asymptote. And it's vertical, it's a vertical line. We'll see what it looks like here in a minute when we actually get to graphing these, but I just want to kind of prep you with what it is. And yes, I know it's a really funny, weird word. You can giggle, it's fine. All right. Find the horizontal asymptote using the rules below. So horizontal, we're talking about, a line going horizontally. This has to do with the degree of the numerator versus the degree of the denominator. Now, what does the degree mean? What is the degree of the polynomial? How do we find that? The degree is the highest exponent. Okay, the degree is the highest exponent. So you might want to make a note of that in case you've forgotten. Degree equals highest exponent. So I don't like talking about degree of P greater than degree of Q. I like to just talk about numerator versus denominator. Okay, P is on the top, so the first case there is that the degree of the numerator is greater than the degree of the denominator. Okay, not the coefficients. Okay, not the coefficients. We're talking about the degree. So the exponent. Okay, so if the highest powered exponent in the numerator is bigger than the highest powered exponent in the denominator, we do not have a horizontal asymptote. So if the highest powered exponent in the numerator is greater than the highest powered exponent in the denominator, you do not have it. If the highest degree in the numerator is less than the highest degree in the denominator, that is y equals 0. Now, let me tell you a little trick to help you remember this. It's not entirely appropriate, but people don't forget it, okay? Y'all know who Dolly Parton is, right? No? You don't know who Dolly Parton is? Oh my gosh. You gotta know who Dolly Parton is now. Abbott is wearing a Dollywood shirt, so it's very, very appropriate. Good choice this morning, Abbott. If you don't know what Dolly Parton looks like, here we go. You need to know. It is important to, don't do that. Okay, she's a very rich woman, okay? Here is Dolly Parton. That's all I'm gonna say, okay? Bigger on the top, right? Her name ends in N, none, okay? Here's the other one. I know y'all know this one, J-Lo, okay? J-Lo, bigger on the bottom. O, Y equals 0. Jennifer Lopez? Pretty sure y'all are pulling my chain.
Oh, that's her. Yeah.
Oh, yeah, her. Yeah.
She's irrelevant.
Okay, anyways. Single ladies, all my single ladies, that's on J-Lo. Okay. Anyways, no, that's Beyonce. My bad, wrong one. See, I don't even know. Never mind. Okay. Well, usually this works to help people remember this, but apparently it's not going to. What? It's not going to help you? Okay. Well, sorry. Maybe it'll help somebody. Anyways, Dolly Parton, bigger on the top, no horizontal asymptote. J-Lo, bigger on the bottom, Y equals 0. I'll just leave it at that. Okay, third case is when the degrees are the same. Okay, when the degree of the numerator is equal to the degree of the denominator, your horizontal asymptote is Y equals the ratio of the leading coefficients. Okay, the ratio of the leading coefficients. So what do I mean by that? Okay, simple case scenario, let's say on the top we have 3x cubed is the highest powered exponent. On the bottom we have 4x cubed, okay? So the leading coefficients there are 3 and 4, so that one would be y equals 3 over 4, okay? That one would be y equals 3 over 4. The last thing that we have to worry about here is something that we call a hole, okay? A hole is a point in the graph where there is a break in the graph. Now, here's the thing. You have to know how to be able to find it because you can't actually see it on your graphing calculator, okay? It will not show you one little missing point on your graphing calculator, so you got to know how to find it. What happens with a hole is not only are you dividing by 0, it is 0 over 0. It means you got 0 in the top and you got 0 in the bottom. That is something that we call an indeterminate form. Indeterminate. It's worse than just dividing by 0. Okay, it is worse than just dividing by 0. Dividing 0 by 0, we really don't know what happens mathematically. Okay, we don't really know what that means, to divide nothing and to split it up into no groups. Okay, so 0 over 0 is what we call an indeterminate form. So that's what's happening when you have a hole. So that was when you had a common factor in the numerator and in the denominator. So after you factor, if you cancel something out, that's where your hole comes from. So to find your x-coordinate, you set what you canceled. Okay, set what was canceled. Equal to 0. Okay, she says set the common factor equal to 0, but the common factor is what you cancel out. And to find the y-coordinate of your hole, you take that x value you just got and you plug it into your simplified function. Okay, you plug it into your simplified function. So that was a big long list of stuff. Let's go through and actually find these characteristics and graph one of these, okay? So let's look at example number 1 there. Step one was to simplify. Can we factor the numerator or the denominator here? No, there's nothing to be factored. So there is no simplifying to be done. Remember, we're not allowed to cancel those x's or cancel those 4's because of the minus in the numerator and the plus in the denominator. So there's no simplifying for us to do here. So our next step is to find our x-intercepts. According to our list, how do we find the x-intercepts? Set the numerator equal to 0. So the numerator is x minus 4. We set that equal to 0. So when we solve for x, we get 4. An x-intercept is always a point. So when you put it on your little list over here, it's 4, 0. The x value is 4, the y value is 0, because the y value is always 0. You're on the x-axis. Okay, after our x-intercepts, we're supposed to find well, let's go ahead and graph that. Let's go ahead and plot that point. Plot that point there on your graph. Okay, put 4, 0 there on your graph. After x-intercepts is our vertical asymptotes. Our vertical asymptotes come from setting the denominator equal to 0. So when we solve this, we get negative 4. When we plug negative 4 into our equation, negative 4 plus 4 is 0. We divide by 0. That's what a vertical asymptote is. It's where your function is completely undefined because you are dividing by 0. Now, when we put this on our graph, we're going to go, it's a vertical asymptote, so it's a vertical line. So we go to x equals negative 4, and we are going to put a dashed vertical line. Okay, do not draw a solid line because it's technically not a part of the graph. Okay, it's an imaginary boundary on our graph. So put a dashed vertical line at negative 4. All right, next one, horizontal asymptote. We compare the degree of the numerator to the degree of the denominator. What's the degree of our numerator? 1, right? We just got x. What's the degree of the denominator? 1. They're the same, so we take the ratio of the coefficients. We didn't have any coefficients here, so it's just 1 and 1, right? X is the same as 1x. So 1 over 1 is 1. So our horizontal asymptote here is y equals positive 1. Make sure that you put y equals. It's a horizontal dashed line at positive 1. Okay, so our graph is starting to take shape here. Next, we deal with any holes. Well, we didn't have any canceling. We didn't do any simplifying. There was no canceling, so there is no hole here. None. Okay. You can have any combination of these. You don't have to have a vertical asymptote. You don't have to have a hole. You don't have to have a horizontal asymptote. Or you could have all three. It just depends on the function. Okay. Now, let's talk about the domain. Okay, let's talk about the domain of this function. We had to exclude the x value of negative 4. That caused our function to be undefined. So our domain is everything but negative 4. So we go from negative infinity. We get super, super close to negative 4, but we don't actually equal negative 4. So we still write that number, but we put the parentheses. Remember, the parentheses means you get really, really close to it. You just don't actually ever equal it. And then we pick back up on the other side of negative 4 as close as we can possibly get to it, but we don't actually equal it. And we go all the way to positive infinity. We're not going to talk about the range. Instead, we're going to talk about the y-intercept. Okay, we're going to talk about the y-intercept because we haven't done that. Okay, y-intercept. I'm on the y-axis. What's true anywhere on the y-axis? X equals 0. So I plug in 0 for my x values. So 0 minus 4 is negative 4. 0 plus 4 is positive 4. So negative 1 is my y-intercept. 0, negative 1 is the y-intercept. Okay, Now, that's all that we're going to find by hand. Now we're going to use our calculators. Okay, so go to your calculator, go to your y equals. Make sure that numerator gets in parentheses, divided by, put the denominator in parentheses. Okay, let's go to the table first and confirm the things that we've got here. We have the 0.40 for our x-intercept, so that's confirmed in our table. If we go to -4, we get an error. That's what's supposed to happen. Our vertical asymptote is where our function's undefined, so that's an error. Our horizontal asymptote, that doesn't show up in the table. We didn't have a pole. Our y-intercept, 0, -1, is right there in our table. So what I'm going to do is I'm going to use my table to give me a few more points to plot for my graph. So like -3, -7, -2, -3, 1, -0.6. Okay, let me get one to the right of my 5.1, and let's get a better one. Okay, 6.2 doesn't give us much there. Okay, let me go to the left of my vertical asymptote. So let me get some points to the left of -4. So -5, +9, and -6, +5. Okay, so I have some points. I think I could graph it, but I want to look at the graph just to kind of confirm what I think I'm looking at. So I can connect these points, okay? What's going to happen, though, is my graph is going to level off right here, the horizontal asymptote. It's going to get really close to it. It's going to get close to the vertical asymptote over here, but it's never going to touch it. Same thing for this piece over here. It's this curve. So I connect these points. Don't connect them with straight lines. It's a curved graph. And I get close to the horizontal asymptote. I get close to the vertical asymptote. And that's my graph right there. Okay. So the reason why we went through all this is because, yes, your calculator will tell you a lot, but your calculator, like with the vertical asymptote, it graphs it with a straight line. It looks like it's part of the graph. It's not really part of the graph. I hate that these calculators do that, but they do. The horizontal asymptote, it doesn't show up. Okay, it doesn't show up. Now, you could, if you wanted to, you could put it in here as a y2, and then just make sure that it fits in between those two curves, because that's what's supposed to happen there. But they will probably ask you about a hole or a vertical asymptote or something like that, and you have to know where it comes from by hand. Okay, let's do number 2 here. Okay, let's do number 2. So step 1, so we're supposed to simplify. Simplifying requires factoring. Can we factor? We can't. We can. It's not going to simplify, but we can factor. Okay, we can factor. We can factor a GCF of 2 out of that numerator. Now, nothing's going to cancel, but I mean, we can factor. Why not factor? Okay. So no simplifying here. Let's go to our x-intercept. Set the numerator equal to 0. You can set it the original part equal to 0, or you can set the factored part equal to 0. It doesn't matter. You're still going to get the same thing. I'm just going to go with the factored part. 2 can't equal 0, so I only need to worry about the x minus 3 equaling 0. So x equals 3 is my x-intercept. So 3, 0 is our x-intercept. Go ahead and plot that on your graph. Vertical asymptote, set the denominator equal to 0. Solve for the variable, so x equals 1 is our vertical asymptote. So over here at +1, I'm going to put a vertical dashed line at x equals +1. Horizontal asymptote, I compare the degrees of the numerator to the degree of the denominator. This is the same case as the one we just looked at. Our highest power in the numerator is 1. Our highest power in the denominator is 1. Look at the coefficients on those terms. So that's 2 over 1, which is, of course, 2. So y equals positive 2 is this horizontal asymptote. So horizontal dashed line at y equals 2. We factored, but nothing canceled, so this one also does not have a hole. The domain for this function, we start at negative infinity. We're good until we get to positive 1. Positive 1 is where our function is undefined. And then we continue on to positive infinity. Our y-intercept, plug in 0 for x. 2 times 0 minus 6 over 0 minus 1. So that's negative 6 over negative 1. Y equals 6. 0, 6 is our y-intercept. 2, 4, 6. Okay, plot your y-intercept. Now we go to our calculator. Numerator in parentheses, 2x minus 6. Denominator in parentheses, x minus 1. My horizontal asymptote was 2, so I'm going to graph that in y2 just so I can see it. First, I'm going to go to my table. I'm going to check what I've got so far. 3, 0. Okay, that checks out. 1, I have an error. Y-intercept, 0, 6. So I'm good there. Now I'm going to look at the graph. I didn't get any extra points, but oops. Okay, let me get some extra points for my table here. Negative 3, 3. That works there. I really just need about 2 points in each part of the graph here. There's that one. Let's see here. 2, negative 2. 5, 1. And look at my graph, make sure everything agrees. Got my horizontal asymptote running through the middle there. Okay. That's what the graph looks like. Okay. Any questions? Okay. Make this methodical, guys. Do the same thing every single time so that it sticks. All right. Let's look at number 3. Okay. Number 3. We're finally going to have one that simplifies a little bit. That numerator, can we factor it? Yes, it's the difference of perfect squares. X plus 1 times x minus 1. Can we simplify? Yes. We got x minus 1 in the top and in the bottom. So our simplified function is x plus 1. What kind of function is that? X plus 1 is linear. Okay, so keep that in the back of your mind for a minute. All right, x-intercept. Set the numerator equal to 0. Well, technically we don't have, it's not a fraction anymore, so it's just the function equal to 0. So our x-intercept is negative 1. Vertical asymptote, set the denominator equal to 0. We don't have a denominator anymore. So this one does not have a vertical asymptote. Horizontal asymptote, compare the degree of the numerator to the degree of the denominator. I always go back to the original for this one, okay? So the degree of the numerator is 2. Degree of the denominator is 1. Bigger on top, so it is none. Okay, we finally have a hole here. Okay, for the hole, we set what we canceled equal to 0. We canceled x minus 1. We set that equal to 0, solve for x, so that says x equals 1. Check it real quick. If we plug 1 into this original equation, we get 1 squared minus 1, 0. 1 minus 1, 0. 0 over 0 is a hole. So That's our x coordinate. We need the y coordinate. We get the y from plugging it into the simplified part of the function. So the simplified function was x plus 1, so we plug in 1 for x there. So 1 plus 1 is 2. Our whole is at 1, 2. It's a whole, so that means we go to that point and we put an open circle. That doesn't look very much like an open circle. Let me try again. At 1, 2, and that's in the wrong spot. Struggling up here. 1, 2. There we go. Open circle at the point. X equals 1, y equals 2. Okay. For our domain, we didn't have a vertical asymptote messing this up, but we do have a hole. Okay. X cannot equal 1. Our x value cannot equal 1. It causes us to be undefined. So there's our domain. Same as the domain of the previous function, if you notice, but we've got a different issue going on here. It's a hole instead of vertical asymptote. Y-intercept. Plug in 0. You can plug it into the original or you can plug it into the simplified. Might as well plug it in the simplified, right? 0 plus 1 is 1. So 0, 1 is our y-intercept. So let me put in the original function, x squared minus 1 over x minus 1. Now, since I had a simplified function, I'm also going to plug that in. Okay, I'm going to plug the original into y1. I'm going to plug the simplified into y2. Let me go to the table. Here's why I'm doing this. Okay, let's check our points. Negative 1, 0, we're good. Our whole at 1, in the original, it gives me an error, right? Because it caused me to have 0 over 0. That's what's supposed to happen. In the simplified version, look, that's the y value that we found. So that's why it's handy when you're doing this to plug in the original and your simplified version, because it will give you the value that you need there. 0, 1 for our y-intercept. Let me get some points here to plot. -3, -2, -2, -1. What does it look like is happening here? It's a line. We're used to the rational functions being curves, but because of what this simplified to, y'all told me that it's simplified to a linear function. Well, that's how it's going to behave. If it simplifies to a linear function, it's going to look like a linear function. Okay, just make sure that when you graph it, that you don't run through your hole there. You got to leave that open space because it's not actually defined at that point. Notice you can't see that on here. And no matter how far you zoom in, you can't see it. So you got to know how to be able to find it.